The 65% factor applied to a computer room load when sizing a standby generator is generally not a code-mandated requirement. It is more accurately described as an engineering safety factor. This factor is frequently employed by engineers during the process of selecting and sizing standby generators intended for use in computer rooms and data centers. The purpose of incorporating this safety factor is to ensure that the selected generator has sufficient capacity to reliably handle the anticipated load demands of the computer room in the event of a utility power outage or other emergency situation. The NEC National Electrical Code provides guidelines for sizing generators, but it doesn't specifically mandate a 65% dirting factor for computer room loads. The NEC does address essential electrical systems and their power sources, including standby generators, in Article 700. It provides requirements for legally required standby systems, which are essential for life safety, and Article 701 addresses optional standby systems, which may include computer rooms. Within these articles, the NEC focuses on ensuring the reliability and adequacy of the power source, but the specific sizing methodology is often left to the engineer's judgment based on a thorough load analysis. The common practice of applying a 65% factor stems from a number of considerations. Firstly, computer rooms and data centers are known for their high power density and critical operational requirements. A power outage can have significant financial and operational consequences. Therefore, engineers tend to err on the side of caution when sizing backup power systems. Secondly, the actual load of a computer room can be difficult to predict with absolute certainty. The equipment within a computer room is constantly evolving, with new servers, storage devices, and networking equipment being added or upgraded regularly. This can lead to fluctuations in the overall power demand. By applying a safety factor, engineers can account for potential future load growth and unexpected increases in power consumption. Thirdly, standby generators have certain limitations in terms of their ability to deliver power. Generators typically have a short-term overload capacity, but operating them at or near the maximum rated capacity for extended periods can lead to premature wear and tear, reduced reliability, and even potential damage. The 65% factor helps to ensure that the generator operates within a safe and efficient operating range. Fourthly, the 65% factor can also account for other loads that may be connected to the generator in addition to the computer room load. These might include lighting, HVAC systems, and other essential equipment that needs to remain operational during a power outage. It is important to note that the specific safety factor used can vary depending on the engineer's judgment and the specific characteristics of the computer room. Some engineers may use a higher factor, such as 70% or 75%, while others may use a lower factor, such as 60% or even 50%, if they have a high degree of confidence in their load calculations and the reliability of the equipment. The demand factors that are referenced, where the first 10 kV are taken at 100% and the remaining at 50%, are more commonly associated with calculating the service entrance load for a building, as per the NEC. This demand factor is not directly applicable to sizing a standby generator for a computer room. When sizing a standby generator, a more detailed and accurate load analysis is required. This analysis should include a comprehensive inventory of all equipment within the computer room, along with their respective power requirements. It should also take into account the operating characteristics of the equipment, such as their inrush currents and duty cycles. Inrush current refers to the high initial current that some equipment draws when it is first turned on. This current can be several times higher than the equipment's normal operating current. Duty cycle refers to the percentage of time that the equipment is actually operating. For example, a server that is running continuously has a duty cycle of 100%, while a printer that is only used occasionally has a lower duty cycle. The load analysis should also consider the potential for future load growth. It is generally a good practice to add a margin of safety to the calculated load to account for any unexpected increases in power consumption. Once the load analysis is complete, the engineer can select a generator that has sufficient capacity to meet the anticipated load demands. The generator should be sized to handle the maximum expected load, including inrush currents and any other loads that may be connected to the generator. It is also important to consider the generator's operating characteristics such as its voltage regulation, frequency regulation, and transient response. Voltage regulation refers to the generator's ability to maintain a stable voltage output under varying load conditions. Frequency regulation refers to the generator's ability to maintain a stable frequency output under varying load conditions. Transient response refers to the generator's ability to quickly respond to changes in load. In addition to sizing the generator, it is also important to consider the other components of the standby power system, such as the automatic transfer switch (ATS) and the distribution panel. The ATS is responsible for automatically switching the load from the utility power source to the generator power source in the event of a power outage. The distribution panel is responsible for distributing the power from the generator to the various loads within the computer room. All of these components should be sized and selected to ensure that the standby power system can reliably meet the power demands of the computer room. In summary, while a 65% factor is not a code-mandated requirement, it is a commonly used safety factor that engineers often employ when sizing standby generators for computer rooms. It is a good practice to ensure that the generator has sufficient capacity to handle the load in the event of a power outage. A thorough load analysis should be conducted to determine the actual power requirements of the computer room, and the generator should be sized accordingly. In addition to the 65% factor, there are other considerations that should be taken into account when sizing a standby generator for a computer room. These include the generator's operating characteristics, the other components of the standby power system, and the potential for future load growth. The NEC provides guidelines for sizing generators, specifically Article 700 and Article 701, which address essential electrical systems and their power sources, including standby generators. Article 700 focuses on legally required standby systems essential for life safety, while Article 701 covers optional standby systems, often including computer rooms. While the NEC emphasizes power source reliability and adequacy, the detailed sizing methodology relies on the engineer's judgment based on a thorough load analysis. The practice of using a 65% factor arises from several factors. First, computer rooms and data centers have high power density and require continuous operation. Power outages can lead to significant financial and operational losses, so engineers often prioritize caution when designing backup power systems. Second, accurately predicting the load in a computer room is difficult due to frequent equipment changes, like new servers and storage devices. Applying a safety factor accounts for potential future load growth and unexpected power consumption increases. Third, standby generators have limitations in power delivery. While they can handle short-term overloads, continuous operation near maximum capacity can cause wear, reduce reliability, and potentially damage the generator. The 65% factor ensures the generator operates within a safe and efficient range. Fourth, this factor can also accommodate other loads connected to the generator, such as lighting, heating, ventilation, and air conditioning, HVAC systems, and essential equipment needed during outages. The specific safety factor may vary based on the engineer's assessment and the computer room's characteristics. Some may use higher factors like 70% or 75%, while others might use lower factors like 60% or even 50% if they are confident in their load calculations and equipment reliability. The demand factors where the first 10 kVA are taken at 100% and the remaining at 50% are usually applied to calculating the service entrance load for a building, as per the NEC, and are not directly relevant to sizing a standby generator for a computer room. Sizing a standby generator necessitates a detailed and accurate load analysis. This includes a complete inventory of all equipment in the computer room, along with their power requirements, operating characteristics like inrush currents, and duty cycles. Inrush current refers to the high initial current drawn when equipment is turned on, which can be significantly higher than the normal operating current. Duty cycle refers to the percentage of time the equipment is in operation. Continuous operation yields a 100% duty cycle, while infrequent use results in a low duty cycle. The load analysis should also account for potential future load growth by adding a safety margin to the calculated load to accommodate unexpected power consumption increases. After the load analysis, a generator can be selected that meets the anticipated load demands. The generator should handle the maximum expected load, including inrush currents and other connected loads. Important generator operating characteristics to consider include voltage regulation, frequency regulation, and transient response. Voltage regulation is the generator's ability to maintain stable voltage output under varying load conditions. Frequency regulation is the generator's ability to maintain stable frequency output under varying load conditions. Transient response is the generator's ability to quickly adjust to load changes. Besides sizing the generator, consider other standby power system components like the automatic transfer switch, ATS, and the distribution panel. The ATS automatically switches the load from the utility power to the generator during an outage. The distribution panel distributes power from the generator to the computer room's loads. All components should be sized and selected to ensure the standby power system reliably meets the computer room's power needs. Therefore, the 65% factor is a common engineering practice for sizing standby generators in computer rooms, ensuring sufficient capacity during power outages. A thorough load analysis is essential to determine the actual power requirements and select an appropriately sized generator. Other factors to consider include generator operating characteristics, system components, and potential future load growth. Additionally, referencing NEC articles such as 700 and 701 provides valuable guidance on essential electrical systems and standby generators, ensuring code compliance and safety. The 65% load factor serves as a crucial element in the design and implementation of robust standby power systems for computer rooms, mitigating risks and ensuring continuous operation during unforeseen power disruptions.